So section 4.3, we are going to study a new situation, a new rule, which we call this multiplication rule. Previously is the addition rule. So what's happening here is, from the meaning, right, multiplication. When this is happening, right? Let's use some example here to explain how this rule to work, right? So we are doing two experiments, everybody, two experiments. So we toss a coin and then we roll a die. Okay, so we want to find out the question here. We want to find out probability of getting a head on the coin, right? And it got a number 4 from the dice. Everybody, is that clear? So you have two events, right? You toss a coin and then you roll a die. And then you want to find out what's the probability for you to get a head on that coin. And also got number 4 on that dice, right? So remember, everybody, probability is what? Is something like something divided by something. So we are doing this step by step, everybody, right? Say we toss the coin, right? We toss the coin. What's the probability for us to get a head, everybody? I mean, I would say it's pretty straightforward, is it right? 1/2, half and half, right? And then when we roll a dice here, right? So what's the probability for us to get a number 4, right? I mean, you know, all the possible outcome here is 1, 2, 3, 4, 5, 6, right? So it's number 4 is one of them. So it's 1/6, right? That's the probability. And then we simply multiply them together to get the probability, what are we asking? Everybody, why we can do that? Why we can simply multiply this probability, right? This 1/2, 1/2, right? 1/6, right? Why we can simply multiply those two probability together, right? Remember this section, what we are talking about, multiplication rule, right? That's based on the assumption. Those two events, they are independent events. Everybody, what's that mean? Independent events, that means those two events, they don't count on each other. What does that mean, right? That means you can understand that as if two events, A and B, right? Which one happening first, doesn't matter. In that situation, A, B, those two events that we say they are independent, right? Let's check if that's the case here, what we are trying to do, right? I toss the coin, I roll a die here, right? We are asking ourselves, the order here matters or not? Like which one go first, which one go second? Do they matter? No, right? I can toss the coin, I can roll a die. That will not impact my outcome here, right? So that's what the reason we say those two events, they are independent, everybody. So whenever we have this independent event, AB, when we calculate probability of A and B, everybody, A and B. So that means like previously, what's the probability of getting a head on the coin? That's A, and getting number 4 on the dice, right? That's A and B. We can simply multiply the probability of PA, which is 1/2 here, right? And then PB, that's 1/6, simply multiply them together to get the probability we are asking. Now, compare with what we just learned, everybody, so that I try to put them together, you don't get confused, right? We just learned that if AB, they are mutual exclusive. If AB, they are mutual exclusive, then probability of A or B, keywords here, everybody? Or, right? Keywords, okay? Or B, right? Is equal to PA plus PB. Remember, that's what we call addition rule, right? Addition rule. That's the multiplication rule. Everybody, they are for different situations. You don't want to get confused. Is that okay? So on the homework, on the exam, I may simply ask true or false. Everybody, if two events A, B are independent, then PA or B equal to PA plus PB. Everybody, is that true or false? Right, that's false, right? You cannot go from here and then go here, right? That's false. Okay, so let me repeat that one more time. So if I say, question, true or false? If A, B, they are independent, then PA or B equal to PA plus PB. True or false? That is false, right? Everybody? So if A, B, they are independent, the correct formula should be this one, right? If A, B are mutual exclusive, the formula should be this one, okay? So hopefully that's more clear. Let's go to use some other example here, all right? So to see how do we apply this multiplication rule. A card is drawn from a deck. Everybody, we are talking about the stats class here, right? We don't require everybody to be like expert in play card game, right? Expert in the casino games. No, I don't require that, right? But I do require you have some basic knowledge, right? How many cards in a regular deck, right? In a regular deck, we usually have 52 cards. Everybody, 52 cards, okay? So why do we have 52 cards? Because we have 4 different, sometimes you call these 4 different color or 4 different shape, is that right? You have diamond, you have heart, you have spade, you have, one more, I forget, right? You have 4 different, we call this suit, thank you, clubs, right? So those are the 4 different suit. How many cards for each suit, everybody? 13. Okay, so you have like 1, 2, 3 up to 10, is that right? And then you have J, Q, K. That's 13 coming from, right? Everybody, follow me? How many cards in a regular deck? 52, right? How many cards for one suit, right? 13, right? And 13 multiplied by 4, we got 52. So 52 is a special number, everybody, right? I mean, maybe not that special for other people, not study stats, but for the people in, stats field, 52 is a familiar number. Why? Because in the beginning of stats, we are using the card game a lot. I mean, to do all kinds of calculation in terms of card game, okay? So that's the one I do require, right? The other example I mentioned earlier, the dice, right? You roll a dice, what's the possible outcome? I mean, 1, 2, 3, 4, 5, 6, okay? Those are the basic items that I do require, right? I don't require everybody to be the expert on the like 21, those like 21 points game, right? No, I don't require that, okay? I mean, we may talk about that later. How do you win that, okay? But the basic stuff, everybody, okay? So now the question here, we are draw a regular card, draw a card, right? From a regular deck. Now you put that back, so replaced, you can understand that way, right? So a regular deck, you have 52 cards, you draw 1 card. Now, after you draw that card, you put that back, or you can understand that as you replace by a new card, the same one, right? And then the second card is draw. We want to find out the probability of getting Q, right, on the first one. I did not write down the whole sentence here, okay? So we want to find out the probability of getting Q on the first card, and then the probability of getting S, right, on the second card. Everybody, that's the question here, right? So you pretty much, you draw 2 cards. You can understand that way, right? After you draw the first card, you want to find out that is a queen, right? And then you put that back. Now you shuffle and draw this again, right? And you want to find out that the second card is A, right? So what's the probability for you to get that outcome? Everybody, let's do that step by step, okay? So first part, let's see, if I draw the card from a regular deck, right? What's the probability for me to get a queen, right? So remember, probability is what? Something divided by something, right? So something here divided by something, right? So the first, how many possible situations we are having? You draw one card out of a regular deck, 52 choice in the denominator. In the numerator is number of cases that we are asking. We want to get a queen, right? So how many queen we have, everybody? How many queen we have a regular deck? 4.
4.
So what we have here is the first piece, right? What's the probability for us to get a queen? It's 4 over 52, right? Similarly, now you put that card back, you have a full deck again, you draw the second card. What's the probability for you to get A here, right? So same as what we have. How many choice you have? 52 in the denominator. And how many A you have for this regular deck you are getting? You have 4, right? So, you can simplify that. 1 over 13, 1 over 13, right? Multiply them together, 1 over 169. That's the answer, right? So the key part here I want to mention is they are equal to the multiplication rule that we mentioned earlier. Why? Because those two events, they are independent. Why do we say that, right? They are independent, everybody? Because you think about that. These two events here, which one happened in the first, which one happened in the second, doesn't matter. Because what the key part here is, after you draw the first card, right, you put that back or you replace that, right? That's the very, very important part. You still got the full deck. Is that clear? So in that case, we can simply multiply that probability to get, okay? Now, that's what we just learned using the multiplication rule.
Professor, I have a question for you. If you were to draw the first card and it was a queen, right?
Yeah.
And you didn't put it back,
yeah,
would the probability change for the ace?
That's right. So we will have the, good question. We have that coming as another example, everybody. So what if we don't put that back, right? So what's happening? You see, I'm so glad that you asked that question, so excited, right? Yes. So what's happening after you draw the first card, right? You don't put that back. So the key part here we can see here is now this, how many cards left over there, right? You only have 51 cards left, right? So that's the one part, right? So let's do that step by step, everybody. Same question, right? Same question. We are drawing two cards, right? The first one, you draw one card from a regular deck. You want to get a queen, okay? What's the probability to get a queen? Let's do that step by step, right? The first one, right? So is you have 4 queens out of a total regular deck, 52 cards, right? That's the answer. That's the probability for us to get a queen. Now, the tricky part here is I don't put that back, right? I don't put that back in a way that I don't have a full deck again, right? I don't have that. How many cards I have left here? 51, right? 51, right? And remember, when we draw the first card, which one we want to get? We want to get a queen, is that right? That's the first one. When we are trying to do this step by step, right? So now the second one, when you try to draw, you want to get an S here, right? Get an A here, right? So out of this 51 card here, right? How many A we have here? We still have 4A. Because the first one here, what we are trying to get here is the queen, right? That's the reason we got 4 left. Everybody, we are trying to do this step by step. I mean, looks like it is still multiplication though. Looks like, is that right? It is a multiplication, but it's not equal to that multiplication. Be careful, everybody. Remember, if you are using that multiplication, should it be what? Should it be 4 over 52 multiply 4 over 52, right? If you are using that multiplication, right? Now the answer is changed. It's 4 over 51, right? Because of that, you don't replace that card or you don't put that card back. Now, so that's the tricky part. How do we answer those questions, right? When they are not independent. In other words, we cannot use that formula, right? If they are not independent, right? So how can we do that, everybody? We can still solve this probability question by using step-by-step approach. So from the homework, you will see like some similar questions doing the step-by-step calculation. You can still find out what is the probability. Everybody? Our last section tonight is this one here, conditional probability here. Conditional probability is one of the advanced topic. So if you are trying to study more stats, right? Say if you are going to graduate school, you will see that again, right? Here, we are giving you very basic introduction, okay? Conditional probability, right? We have this formula here. How do we read this, right? So it's read this as probability of like the event A is happening given this vertical bar here, this vertical bar here. So how do we read this formula, right? I mean, it's probably the first time for you to see this notation, right? This vertical bar here, how do we read this? So we can read this, the probability of the event B is happening given. So this vertical bar read this as given, A is happening. So in other words, they provide you some extra information about, like, you know, that event is happening. So that extra information, right, may change your final answer. That's the tricky part. That's what we say, conditional, right? They have some extra condition given here. Okay, so the formula here is equal to probability of A and B. So what does that mean? Probability of A is happening, also B is happening, right? That's the meaning here. Divided by probability of A. Everybody, be careful in terms of notation here, right? So here we are asking probability of event B is happening given A. So given something divided by something. You don't want to divide by probability of B. Okay, so that's the one part I want to emphasize that here, all right? And then we are going to apply some example here to understand how do we apply this conditional probability formula to solve those probability questions, okay? Let's see. Let me continue. Forget this paragraph here, everybody. Forget this paragraph here if that will confuse you, okay? Can temporarily forget this piece here. Also, if that confuse you, do not worry about that. Okay, this example here is not a good example. I was trying to see, yeah, forget this example. No, this example is somehow might get you confused. Let's use another example here to explain how do we use the conditional probability formula to solve that. Everybody? So this question here, We are given the information about 100 people. And out of these 100 people, we are asking some yes or no question. And from the respondent, we find out, so like the table we are given usually is like this 4x4 table here, like that, right? So how do we understand that? We have 32 male, right? They answer yes, right? And then 18 male, they answer no, right? You can understand that way, right? And then we have 8 female, they answer yes. 42 female, they answer no, right? I mean, we didn't explain, I mean, which kind of question they're asking, right? I mean, we are not worried about that, okay? So, I mean, based on the information we are given, here is, those are the information we are given, 2x2 table here, right? So on the homework, on the exam, you have to do some calculation by yourself, everybody. What's the summation of the total for each row, right? How many female? How many male, right? Well, 50, 50, well, happen to be the same, right? I mean, not always. And then how many people answer yes? You add them together, 40. How many people answer no? 60, right? And then when you add 50, 50, you got 100. When you add 60 plus 40, you also got 100. Everybody? So that's the information we are given, okay? Now, we want to, out of this 100 people, right, we randomly select one person, okay? Randomly select one person out of this 100 people. We want to find out the probability of that person answered yes, given that person is male. Everybody? You see the tricky part here, right? So given that person is male. So it's like extra information, right? So let's say, say temporarily, if we don't use this information, everybody, say like, forget this one for the moment. How about that? Let's see what's the probability, right, for us to randomly select one person out of these 100 people, right? What's the probability of that person answer yes? Let's check out. Everybody, is that fair, right? Let's temporarily not using that, this extra information here. So we don't know that, okay? We randomly select one person out of these 100 people. We want to find out what's the probability of that person answer yes. Okay, remember, probability is what? Something divided by something, right? You randomly select one person out of 100 people. How many cases altogether? 100 in the denominator, right? And then in the numerator is what we are asking. We're asking how many people they answer yes. Everybody, how many people they answer yes? 40, right? I may see some people, they already know the answer already, right? It's 40 over 100, 40%. Is that clear? So that's the information. If we don't use that, okay, we cross that out. We don't know that a person is male. That's the answer we are getting, 40%, okay? Now, what if we use that, right? This extra information. Everybody, you will see that we are change our answer, okay? So how do we solve that? Let's do that step by step, right? So, I shouldn't even remove that, right? This one is 40%, this one is 40%, right? If we don't have this extra information, right? Now, with this extra condition information, right? So the formula we just learned, right? Probability of A given B, like that, right? So to match this question here, I'm going to use Y to indicate that person answer yes, right? Y for yes. Event M for that person to be male, okay? So the question here is we want to find out probability of Y given, everybody, given that the person is male. You see that? So that's we translate into like human language to the mathematical formula, right? So remember the formula is what? You're given something, you divide by something, right? Divided by probability of M, probability of a male, right? And the numerator is male and answer yes, right? So we calculate the probability of each, everybody. If I randomly select one person from the 100 people, right? What's the probability for that person to be male? That's this one here, right? PM. Probability of that person to be male, right? So probability is something divided by something, denominator 100. Numerator, how many? Male. That are we asking here? 50, right? Yes. So 50 over 100. That's for this denominator, probability here. And then in the numerator, we are asking, right? You select 1% out of 100, the same, 100. This part here is how many people they answer yes. Also, that person is male, everybody. So how many people here they answer yes, and also that person is male? You know, that's 32, right? So the answer here is 32 over 100. That's the probability in the numerator, okay? Probability in the numerator. So we solve for that. What's the answer we are getting? 64%. Check, check, check. Right? 64%. With this extra information, we know the probability of that person answer yes is 64%. If we don't use that information, everybody, what's the answer? 40%. You see? So that's the fundamental rule in statistics, everybody. If some extra information will change our answer, right? Change our probability, right? We should use that. That we should be able to get, sometimes higher, sometimes lower, but we have a different probability. We should use that. Okay, so that's the, for this question here. Is that clear, everybody? We have one more session here, then we are, one more part, small section here, then we are done for the week. Let's see, the last piece, the last but not the least, right? Well, we happen to have this at the list. And this is one of the most difficult words for me to pronounce. At least probability, right? This is a very common question that you see that in stats, right? Whenever you see in a question, they're asking something, something at least, blah, 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 right? Remind you, we should use considering this complementary event approach. Usually that's easier. Okay, why is that? Let's do that, okay? So this question here, so a coin is tossed 5 times, regular coin. If they don't mention that, that means it's a regular coin. If it's a special one, they will specifically mention that. Otherwise, if they don't mention that, it's a regular coin, 50-50 breakout, right? So you toss the coin 5 times, find out the probability of getting at least one tail. Everybody, think about that sentence here, right? At least one tail. Right, that means what? That means you will get 1 tail, 2 tails, 3 tails, 4 tails, 5 tails, right? I mean, all those are possible, is it right? I mean, that means at least 1. Right? So we need to calculate what's the probability for us to get like 1 tail, right? Find out that, right? Similarly, find out what's the probability of the 2 tails, and then what's the probability of 3 tails, and so on. And then add them together, right? That's one way. You can imagine if you try to do this, everybody, it's going to be difficult. In fact, if we are trying to do this way here right now, is beyond our knowledge. We haven't learned something yet. So we cannot solve this directly if we try to find out probability of one, probability of two tails, probability of three tails, and so on, right? It's not that easy. Everybody, you think about like 1, 2, 3, 4, 5, 5 coins, right? 5 position, right? Right. Say you have 2 tails. So you think about that. You want that 2 position to be tail, right? Could it be here? Could it be here? As one case, right? Could it be here or here, right? Those are 2 tail. Or could it be here or here, like that? You know what I mean? So there are many possible situations. It's not that straightforward here. Okay, so that's the reason why if we are trying to solve this directly, it's not that straightforward. Okay, 1, 2, 3, 4, 5. Okay, now we have another way to solve that. Okay, so which is the one that we mentioned earlier, using the complementary event. Complementary event, right? So everybody, think about this statement here. We define this as an event or statement. You can think in that way, right? That is a statement say, we want to get at least one tail, one statement or one event, okay? Think about the opposite statement or the complementary event, right? What's that mean? What's that mean? So the opposite of that statement here, at least one tail, the opposite will be like 0 tails, right? Think about that, everybody. Follow me? The opposite. 0 tail, that means what? That means those 5 positions here, you have 0 tail. That means what? All should be head. Is that clear? All should be head. All those 5 positions should be head. That's this complementary event, the real meaning, right? When you say 0 tail out of the 5 tosses, that means every single toss, you need to get a hat, right? So that's the PA hat, right? Now, if we can try to find out what's the PA hat here, then how do we solve PA here, right? That's the probability of at least one tail, right? We are using 1 minus the PA bar. Follow me? So how do we find out the probability of A bar, right? Probability of getting 0 tail, like this case here. Find out what this case to be happen, what's the corresponding probability? Everybody, the first coin, what's the probability for you to get a hat? 1/2. Second coin, what's the probability for you to get a hat? 1/2. Third one, same. Fourth one, same. Fifth one, same. Everybody, independent. Just 5 coins, toss 5 times. Doesn't matter which one first, which one second, right? So we multiply them together. That's what we call the multiplication rule, right? So that's the probability of A bar, everybody. So that's equal to what? 1 minus 1 over. You multiply those 2 together is equal to 32. So 1 minus 1 over 32, using the high school algebra, right? So 1 is equal to what? 32 over 32, right? Minus, that's 1 over 32, right? So it's 31 over 32. Follow me? That's the answer. Everybody? So using this complementary event, right, we are able to solve this question relatively easy. So in other words, what is my key point here? Whenever you see in a question, they have these keywords, at least, right? Probability of blah, 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 at least, blah, 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 right? That means what? Think about the complementary event. Usually that calculation might be much easier. Not like the one we are trying to do in the beginning. If we are trying to do this directly, turns out to be difficult.